we're going to look at 3, 7 in two parts, okay, today and tomorrow. The first part today is going to be kind of the more simple part because it's a shorter day. Tomorrow we look at more of the more elaborate part that kind of looks at that infinity part again. And so let's get started with a little review, and we're going to have to do a lot of thinking here, so be ready for that. So let's zoom in a little bit. There we go. All right, so let's look at, consider 1 over n, right? What do you think will happen to this as n gets really big? Okay, what will that number eventually be? So if I have 1 over 2, 1 over 3, right? 1 over 4, what is happening to the numbers? Again, smaller, right? So hopefully we could recognize as the denominator gets bigger, the number gets smaller, right? This is 0.333. Then it goes to 0.25. That's getting smaller, right? 0.2, it's getting smaller. So a bigger denominator means a smaller number. Now, if we kept going to this forever, where would we end up? What does it get close to? 0. Does it ever actually equal 0? Never, right? That's why we call this a limit. Okay, a limit. So it's not actually going to be 0 at any point, because the only way to get 0 would be if the numerator was 0, and we can divide by anything, and the answer is 0. But since the numerator is 1 everywhere, we'll never get an answer 0, but these will get infinitely close to 0. So we call that a limit of 0. Okay? It's the number we kind of get very close to, and never actually equal to. Okay. So it appears that the limit is 0. So let's try something in the neighborhood for the limit equal to 0. So we're just going to look at this and say, you know, what happens, or how close do I have to get here? Our main question that we looked at yesterday was, when does this happen? What term? Like, this is the first term, the second term, the third term, the fourth term. How many terms do I have to get this close? 1/10 away from 0. Okay? So we did this. This is just a review, and you can just jot it down along with me. So we have 1 over n is somewhere between these two numbers, right? And this could be written a number of ways, right? My limit is 0 and plus or minus the radius, or h, right, which is 1/10. Right? That's another way of writing it, the p and h that you saw on the back of your homework. Right? And then we just solve these individually, right? We said, well, what happens with this first inequality? And we get, let's see here, negative n less than, what, 10? So this one says n must be greater than negative 10, which should raise a red flag because n is these numbers. They're counting numbers. So to say it's bigger than negative 10 doesn't make sense, right? Well, it can't be negative 9. There's no such thing as a negative 9 natural number. We always start on a sub 1 and go a sub 2, a sub 3. No negatives, no decimals, no fractions. So we kind of just, okay, let's look at the other inequality and see if that tells us something more revealing. And we do very similar steps, right? And this says we have to be above the 10th term, and then we interpret that that's going to be on the borderline of the neighborhood. This is like if there's this neighborhood and there's a gate, it's at 10. But to actually be in the neighborhood, we have to get to 11 or above. Right? So there's a little quick review of everything you did for your homework. But notice we get a certain number here, 11. Okay? And if I throw that into my Desmos, right, 1 over n, right, and it was negative 1/10, or negative 0.1, and positive 0.1, you can verify. Right, and you can see there's my neighborhood. There's a 0 plus a 10th minus a 10th. Right? Yeah. And then once we get over here, we can see 10 is we're at the gate of the neighborhood, and 11 is when we're actually inside the neighborhood. So this is the valuable part of using this, and you actually see what you're doing, you know, and your answers, and why we go from greater than 10 and why we choose, you know, greater than equal to 11 as our actual answers, right? So, any clarifications needed on that so far? Right, is there anything we need to revisit or clarify, or how come this, what if that? Maybe, you know, any of those type of questions. It's a good time to ask. Now, I'll take that as we're good. Go ahead and do it for 1 over 200. What do you predict will happen with this number if we make this value here even smaller? Right? Because again, this is a bigger number on the denominator, therefore it's a small number. What do you predict will happen to our answer before you do it? All right, and then go ahead and solve it and see what you get. There it is. All right. So you'll notice we made this number smaller, right? And later on, we're going to start calling this number right here epsilon, right? That's a general Greek letter we use when we do this plus or minus bit. It's called H in our last homework, but we kind of changed it up a little bit and called it epsilon here. So if I make this neighborhood, like if I close my neighborhood down a little bit, right? And I say I want my neighborhood to be even smaller, you see that it takes longer to actually get to the neighborhood, right? We have to go way, way, way down. So what you want to do is start developing an intuition of smaller numbers mean it takes bigger ends to actually get there. I'm at 100 right here, and I'm still not inside, right? And as you saw when we were solving, we actually have to go to the 200 and first term to actually make it inside the neighborhood. 200 gets you to the door or to the gate. 201 gets you inside. Right? So there's this relationship. The smaller these numbers get, the bigger end that's necessary. Our goal between today and tomorrow is to come up with formulas that predict this number exactly. If I tell you what the epsilon is, can you tell me what n is required to get inside the neighborhood? And that's actually a simple way of stating a very complicated calculus question that we want to be getting really, really, really good at. Okay, so I'm planting the seed right now. We're going to come back to it tomorrow and talk about the epsilons and talk about, you know, how to actually do all these proofs, right? Because it's going to take a little bit longer. So I'm just planting that seed right now. Okay, so leave it at that, and we'll get to it tomorrow. Okay. Now, flip it over to the next part and we'll talk a little bit more about where do these things end up. Okay. Where do these end up? So we were able to, on the front, just to kind of look at this, 1 over n, that's 1/3, 1/4, 1/5. Okay, that's going to go to 0. I can just kind of figure that out by some common sense. What if we have some more complicated expressions here? How do we deal with those? How can we figure out limits? What happens in infinity without having to graph it, without needing to graph it? That's the question to answer here. And there's two things that can happen. It gets close to a number and it converges, right? So it converges if it gets close to an actual number. or it doesn't get close to a number at all and it diverges. So consider these opposites of each other. So sequences without limits, they diverge. They don't have a limit. Okay, so the limit does not exist. Okay. Now, most of your graphs and functions you've worked with your whole life are all divergent. So go back to graphing straight lines. You will remember that your teacher probably always told you put arrows on here because it goes on forever. It goes on forever in one direction, gets positive, goes in another direction, gets negative, and never just slowly slows down and gets to a certain number and says that's as high as we're going. It goes on forever. It diverges. It keeps on going. Right? Same thing with your parabolas. You know, on both sides, they just keep on going positive, positive, higher and higher and higher, both going to the right and going up, right? Or going to the left and going up. Right? So those are divergent. So just kind of as a frame of reference, a lot of the graphs you've worked with your whole life, they diverge. Only in Algebra 2 did you get to some that started having what you guys might remember as horizontal asymptotes. They kind of level off at some point and they don't get below some value, right? These are the converging ones. They get closer and closer and closer and they don't touch. So if you want to think of if it converges, for now, loosely, you want to think of horizontal, right? Asymptotes. And you saw those in Algebra 2. Because those are the graphs that it gets closer and closer and closer, but never actually crosses it, right? It stays above that imaginary, line or dotted line when we graphed it. Okay? All right. So for a lot of these functions, these are the types of functions that you graphed in Algebra 2, and we just want to say, well, what happens? You know, how do we know? How do we figure it out? And there's a little trick that we use to solve that problem. So, you guys remember what the degree of a function is? Do you know what that is? So, the degree of a function is the highest exponent, basically. So, what we're going to do is a little trick that helps us figure that out. All right, so, on these, what we can do is say, let's just take the highest degree of each of these, and what I want you to do is this. Go ahead and write this function down, like so. Leave a little space. And then put the fraction bar. And here's what we're going to do. We're going to divide every single term by the highest degree. In this case, it's just n. Right? If this was n squared and this was n, we would have divided by n squared. So you just look all over the top and bottom, numerator, denominator, find out what the highest exponent is, and we're going to go through and just divide by that everywhere. Everywhere. And we'll have certain things cancel, right? Just like normal. So like those ends cancel, these ends cancel, so we have a 2 and a 1. Now, these are just ordinary ends. We're thinking about a very, 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 very large number. Let's call it infinity, right? If we have the same size infinity top and bottom, it's kind of like they cancel out and we're just left with 2. Here they just cancel out, we're left with 1. As we saw in the front, though, what is 1 over n if n's a very, very large number? Right, what did we say the limit was of 1 over n? Yeah, we get a limit of 0, right? It's not going to be, exactly 0, but it's, 0.0000000, 1. That's basically 0. So we could just call these, both of them, right? It doesn't matter if it's a 1 or a 5. Right? If you're doing an infinitely bigger number, these are going to be infinitely small answers, right? So these just turn into zeros, and then we're left with a couple numbers that tell us our limit is 2. And we haven't answered the question. If we get a number here, since we've got a number, we know it's convergent. It converges, because it just says state. It doesn't say state what the limit is, it state if it converges or not. So we have to say it's convergent. And like before, use the tools that you have at your disposal. I'm just going to keep on reiterating this so we can put this in here and visually see. You know, think of it like as if you want to know the answers to the questions of the homework, this is how you get them. Because you can visually see it. Go back, go back, go back, go back. And then you can see it. Ah, yeah. It's, where is it approaching? It's getting closer and closer to 2. Right. And convergent, you're thinking horizontal asymptote type of thing. It's not exactly the same thing, but they have some similarities. All right. So this is going to be your main problem for today. Is just saying that, right? Going through and using this technique. All right. So go ahead and try one. See what you get. And it doesn't matter that this is an n squared on the bottom, it just gets to 0 even faster than if it's just regular n. All right? So check mine and see if that's what you got, something similar. And then try 2. See what you get for 2. All right. So, once you get here, what do you get on the bottom? 3 over n as n gets infinitely big. What does that equal? 0. What's 1 over 0? Yeah, can't do it. So that's how you know if you get this undefined thing going on. That's how you know it's divergent. Okay? So you got a couple examples of it gets to a certain number, but as soon as it's divided by 0, that old pesky divided by 0 shows up in math, you know that the limit does not exist, and this is divergent. So it would actually say it equals, undefined, and therefore it diverges, or divergent. And if you look at this, you might spot this, say, well, n over 3, that's the same as like 1/3 n, right? Which most of your mathematical experience, you don't use n, you use x, right? So this is just the graph of y equals 1/3 x. This is just a up 1 over 3, and yeah, as I mentioned before, those are divergent. If it's just a straight line, it's just going to go up and up and up forever, right? It's not technically a line because these are only natural numbers, so really it's just the dots, like you see on the decimals. It's not really a line, but you can tell these dots, and there's no negative because it starts at technically 1, and then just goes 2, 3, 4. So it's not really a line's going forever, but these points keep on going up forever and never actually hit a horizontal asymptote anywhere, and just keep on going and get lost. Okay. So what we just did is that we just pretended that these numbers just get infinitely big, right? And there's a special way of writing that down, and that's what this notation is, right? Saying, so what we're going to do is throw this new notation saying, pretend n is just getting infinitely big, and we're going to put that in front of these problems. Because that's what we're really doing. Like, how can you just go through and just divide everything by, whatever you want, and just say, like, oh, 3 divided by n squared, well, that's now equal to 0. Well, it's not really equal to 0. It only gets super close to 0, and that's why we need this new notation in front of those problems, because it tells us it's okay to do that. Okay? So we have this new notation that the limit, abbreviated LIM, and please say limit, don't say lim. I know some people still say cos instead of cosine. This is abbreviation. You don't say the abbreviation. Like, my name, you wouldn't say, if I say this is my name, you wouldn't say my name is Merhagen. This is what happens if you're saying cos or sin. You're saying, oh, Merhagen, can you help me please? Merhagen. You don't actually announce the abbreviation. It stands for something else. So, limit, cosine, sine, not lim, sin, and cos. Got it? All right, and we got to practice for the first time. This little symbol here, it means approaches. We don't put equals there because we can't put the next thing afterwards. But that approaches. Gets infinitely close to infinity sign. So you guys get to start writing these infinity signs in your work now. So it gets really close. And this is going to be, of course, it says, whatever's in the little curly brackets. In this case, it just says A of n. It just stands for any of these things inside. Okay. And it's going to equal some number, L. So on these previous problems, these are the L's. So L equals 2, the limit equals 2, or the limit down here equals 1, or the limit, if it diverges, we could just say it does not exist. Okay, there is no limit. Okay, it's weird, we get an answer of undefined because we're dividing by 0, right? But we would say the limit actually does not exist. So on this one, we would say limit does not exist. You would not say the answer is undefined, because it's not asking you that question. It's asking you, what is the limit, right? So we say there is not one. Okay? So a few theorems that are just true. Okay. First is the one we just did on the front, and we use it over and over and over. If we're dealing with 1 over n or 1 over n squared, and this n on the bottom gets infinitely bigger, it just gets closer and closer to 0, right? So we're okay with that. You guys kind of put that together, with right up here that you just saw. 1 over n, bigger numbers makes a smaller, right? Bigger denominator makes a smaller number. Okay. Now, limit of k. That means k is any number. It's just a number, though. There's no n, right? So if there's no n in the problem, it's just going to stay there at k. So k would be like y. If I graphed y equals 2, and I said, what's the limit of 2? Well, y equals 2 is just this. Just a horizontal line. Of course, the limit's going to be 2 because that's where it is. It doesn't matter if n goes to infinity, right? There's no n over here. It's the same thing if I ask you, what's the slope of, y equals 2? Well, there is no slope. It's not going anywhere. There's no x to work with, right? There's no n to work with here. It's not going anywhere. It's just staying flat. So if we happen to just have a constant number, right? And every time you hear the word constant, just think number without a variable. It's just any random number, right? It's going to stay there. It's not going anywhere. So small things. This one's more useful to us than this one, but just so we know, there's a difference. Okay? So let's go through. Let's start the first one, but all we're going to do is just practice now incorporating this new lingo here in our problems that when we're doing them, we're going to say, let's take the limit as n approaches infinity and do the same thing we did above here. So I'm going to rewrite this. If you have different colors, feel free to use them. It's kind of nice. Find the biggest degree. In this case, they're both n. And divide everything by n. And so the real reason we're able to do the next stop is now we're putting this here. These infinite, really big numbers cancel out. So do these. So we end up with 3 and 1. And these 7 over n or 5 over n, when we're talking about really big numbers, the number on top doesn't really change anything. The fact is 7 divided by a super billion and then 5 divided by a super billion, they're still just basically 0. Very small numbers that don't change the direction of this. So we get an answer of 3. So our limit of this a sub n, this limit of this function as n goes to infinity, equals 3. And by all means, check it. Right? Make sure it makes sense and what your answers mean. You can go back here, type it in no time at all. And you can see roughly it's approaching 3. Just got to zoom in a little bit, but it's getting closer and closer. It's not too close to it, but it's getting there. So the question tomorrow is, well, how close do if I want to have a very small neighborhood, what's the right size n? Like, I could keep on doing this, but the n might be in the tens of thousands. That's the question for tomorrow, is that if I want to be within, let's say, 0.001 of 3, above or below, what value of n do I have to get there? And I don't want to have to graph it and scroll until I finally see it cross the gate into the actual shaded area. I want to be able to calculate it. So that's tomorrow's question. But we can definitely see it's getting closer and closer to 3. Okay, so that should confirm your answers and say, okay, that makes sense. And that way, as you're going through this, if something doesn't seem right, you have a way of checking to make sure, okay, sometimes things don't seem right, and you're like, well, I guess it is. That my work matches the graph. Okay, I'm just got to be okay with that. And other times your intuition is like, no, something's wrong, and then you check the graph. Yeah, something is wrong with my work, and you can go back and find it. Okay. Someone asked the other class, so I'll bring it up here. What happens over here if you get 0 over 0? Right? Normally that would equal 0, but if both of them are 0, there's a whole different process of going through and finding out what really happens. So that is all these little things, like if you start wondering, what if this? Well, what if that? And like, well, there's usually a separate day or separate technique or a separate formula for all those different cases. What if these are trig functions, right? We looked at, lines and parabolas and, things that have horizontal asymptotes. What if they're exponential functions? Like, what if they're logarithm functions? What if they're square root functions, right? All that stuff, okay? So, very cool stuff to all think about. So go ahead and finish B, C, and D. Check with each other. See what you get. Pull out the Desmos. See how that confirms or, or not. And then you can change it if you need to. But you want to get a good idea of how all this stuff works. And I'll give you a second to wrap yours up and see if you got what I got. Encourage you to go back and put each of those into Desmos and see what it looks like and see what's happening here for each one. What does a divergent, graph look like? What kind of graph is this? Is it a parabola? Is it a line? Does it have asymptotes? What is it? Okay. All right. So I'm going to post a little assignment from the book, and you got a little bit of time to work on that. And then if you didn't finish anything from the homework last night, you want to catch up. You don't want to get behind on this. Okay. Use the library, use me, I'm in here in the mornings, and all that good stuff. Use each other.